Hello everyone. Today I will be doing a short presentation on the Euclidean algorithm. The Euclidean algorithm is a method that is used to compute the GCD of two numbers. For today's talk, I have prepared a few slides with the help of which I'm going to present. So let me share the slides with you. Before I begin my presentation, I would like to thank a few people, including my father, who has helped me immensely in preparing the slides and also has taught me the concept of the Euclidean algorithm. I would also like to thank all teachers, especially Saisa, who has encouraged all of us to embark on such a project and has given us references to very useful books in mathematics, physics, as well as in chemistry. The Euclidean algorithm is one of the oldest algorithms in common use. It appears in the book called Euclid's Elements, which has been written in the year 300 BC, specifically in Book 7, Propositions 12, and Book 10, Propositions 23. Let us start by giving you a brief notion about the divisibility of numbers. So if we take two integers, a and b, where b is not equal to 0, we say that b divides a if a is equal to bc for some integer c. So this vertical line in the middle means that b divides a. Here are a few examples. 2 divides 4 because 4 is equal to 2 multiplied by 2. 13 divides 39 because 39 is equal to 13 multiplied by 3. 20 does not divide 61 because 61 is an odd number and therefore cannot be written as a multiple of 20. The division algorithm. The division algorithm gives us a criteria for the divisibility of numbers with respect to the remainder. If we take two integers, say a and b, where b is not equal to 0, then there exist integers q and r such that a is equal to bq plus r. Moreover, if we impose the restriction on r, saying that r is greater than or equal to 0, lesser than or equal to b minus 1, then integers q, r are uniquely determined and are called the quotient and the remainder of a upon division by b respectively. Note that b divides a if and only if r is equal to 0. Again, I've given a few examples here. 4 is equal to 2 multiplied by 2, where a is equal to 4, b is equal to 2, q is equal to 2, and r is equal to 0. 39 is equal to 13 multiplied by 3, where a is equal to 39, b is equal to 13, q is equal to 3, and r is equal to 0. 61 is equal to 20.3 plus 1, where a is equal to 61, b is equal to 20, q is equal to 3, and r is equal to 1. So in this case, 61 is not divisible by 20 as the remainder becomes 1. The GCD of two numbers. So if we take two non-zero integers, say a and b, a positive integer d is called the GCD or the greatest common divisor of a and b if it satisfies the following conditions. So d has to divide both a and b, and if e is another common factor of a and b, then e has to divide d. Only then we can write d as the GCD of ab. It is not difficult to show that d is unique, and I leave this as an exercise for now. Here are a few examples. So the GCD of 2 and 4 is equal to 2. GCD of 13 and 17 is equal to 1. GCD of 26 and 82 is equal to 2. Now we finally come to the Euclidean algorithm. So let us again take two non-zero integers, a and b. The GCD of AB is the last non-zero remainder, Rk, obtained by the following successive steps of division algorithm. These are the successive steps of division algorithm. In this case, we are dividing a by b. So in step 0, we get a is equal to b dot q naught plus r naught, where r naught is the remainder and has the property which says that r naught is greater than or equal to 0, lesser than or equal to b minus 1. This property can be obtained from the division algorithm. In step 1, B becomes the dividend, whereas R0 becomes the divisor, and we write B as R0 dot Q1 plus R1, where R1 is again the remainder, and has the similar property as the preceding remainder. In step 2, R0 becomes the dividend while R1 becomes the remainder, and we write R0 as R1 dot Q2 plus R2. Following this procedure for subsequent steps, we finally get that the remainder becomes 0. So the last non-zero remainder, that is Rk, is taken to be the GCD of A and B. Now let us discuss the proof for the Euclidean algorithm. We already know that Rk is the last non-zero remainder obtained in the process of successive divisions. So it is enough to prove the following three statements, which say that the remainder becomes 0 for some step in the process of successive divisions. Rk is a common divisor of A and B. Every common divisor of A and B divides Rk. Let us prove the first statement. Here we have a string of inequalities among the remainders of successive division steps. So each remainder is strictly smaller than the remainder in the preceding step, and all the remainders lie within 0 and b minus 1. So here's 0 and b minus 1, and the remainders lie in between 0 and b minus 1 in an order of decreasing magnitude. There are only finitely many integers between 0 and b minus 1. Therefore, one can assert that there will be a stage when the remainder has to become 0. However, the validity of this statement requires the well-ordering principle of natural numbers. Coming to the second statement, where we need to prove that Rk is the common divisor of A and B. In order to prove that Rk is the common divisor of A and B, we start from the bottommost step of the division algorithm. Here, one can clearly see that Rk divides Rk minus 1. So moving on to the preceding step, one can also see that as Rk divides itself and Rk minus 1, it divides the right-hand side of the expression and also divides Rk minus 2. With a similar argument, we move on to the preceding step and prove that Rk divides Rk minus 3. Continuing this procedure, we can finally prove that Rk divides both A and B, being the common divisor of A and B. Now, we need to prove that Rk is the greatest common divisor of A and B, and in order to do so, we consider D as another common divisor of A and B and try to prove that D divides Rk. So for this, we start from step 0. Here we know that D divides A and B, hence D divides B dot Q naught. So if we take B dot Q naught to the left-hand side of the expression, it follows that D divides R naught. Similarly, in step 1, D divides B and D divides R naught. So D also divides R naught dot Q1. Similarly, if we take R naught dot Q1 to the left-hand side of the expression, it follows that D divides R1. Now, if we continue following this procedure till step k plus 1, where D finally divides Rk, we are done with the proof for the Euclidean algorithm. Now, here are a few examples for the Euclidean algorithm. Let us take A as 426 and B as 300. So upon dividing 426 by 300, we get 426 is equal to 300 multiplied by 1 plus 126 in step 0, where 126 is the remainder. Similarly, we continue doing this till we get the last non-zero remainder, that is 6. And as we have seen before, 6 is the GCD of 426 and 300. The second example, we take A as 47 and B as 30. So upon dividing 47 by 30, we get 47 is equal to 30 multiplied by 1 plus 17, where 17 is the remainder. Again, we follow the same procedure till we get the last non-zero remainder, that is 1. So 1 is the GCD of 47 and 30. The Euclidean algorithm also gives us a proof of the fact that if D is the GCD of A and B, then there exist integers x and y such that D is equal to A multiplied by x plus B multiplied by y. In other words, it proves that the equation A dot x plus B dot y equals to D has non-zero integral solutions if D is the GCD of A and B. The Euclidean algorithm does not require prime factorization of integers and is therefore more preferable over other methods involving the prime factorization of integers. The Euclidean algorithm is also true for polynomials in one variable. By this, I end my presentation.